Assalamu alaikum, brothers and sisters, welcome to the journey of quest, where we quench your thirst of knowledge. Have you ever wondered how mountains form or why certain rocks look twisted and contorted? Beneath the surface of our seemingly solid and static world, there's an unseen power constantly at work. This power shapes the land we walk on, forming towering mountains and deep ocean trenches. It's the force that transforms ordinary stone into gems, and it's the reason why rocks can appear twisted and contorted. This power is strain, and its study is known as strain analysis. Strain analysis is a fundamental technique in the field of structural geology and geotectonics. It allows us to understand the forces that shape our planet. But strain is not just about the visible changes we see on the surface. It's about the invisible transformations happening deep within the Earth's crust. It's about the immense pressures and temperatures that can reshape entire landscapes over millions of years. In strain analysis, geologists examine rocks and minerals to determine the amount of deformation they have undergone. They study the changes in size, shape, and orientation of these geological structures, all of which provide clues about the forces that have acted upon them. This information is essential in deciphering the history of rock formations and can help predict future geological events. You see, every rock tells a story. It may tell of a violent volcanic eruption or of the slow, steady pressure of tectonic plates. It may speak of an ancient riverbed or of a mountain range that once towered high but has now eroded away. Strain analysis is the tool that allows us to read these stories, to understand the events that have shaped our planet's past, and to anticipate what might come in the future. So, as we delve deeper into the realm of strain analysis, remember this. Every twisted grain of sand, every contorted pebble, every crumpled layer of rock is a testament to the immense unseen power that shapes our world. Strain analysis, in essence, is the key to unlocking the secrets of our Earth's past, present, and future. So, how do geologists go about analyzing strain in rocks? Great question. The strain analysis process is a meticulous journey that begins with the collection of rock samples. This is an adventurous stage where geologists trek through varying landscapes, drilling into the Earth's crust to collect rock specimens. Each sample collected is a piece of the Earth's story, waiting to be read. Once the samples are collected, they're ferried back to the lab for analysis. Here, the rocks undergo a series of tests to expose their hidden secrets. The first technique utilized is optical microscopy. This is where a thin slice of the rock, known as a thin section, is placed under a microscope. This allows geologists to closely observe the rock's mineral composition and structure. It's like peering into the inner workings of our planet on a microscale. Optical microscopy, however, is just the beginning. The rocks then undergo X-ray diffraction, a powerful tool that provides detailed information about the crystallographic structure of the minerals in the rocks. By bombarding the sample with X-rays and measuring how they're diffracted, geologists can identify the types of minerals present and their spatial arrangement. This information helps geologists understand the conditions under which the rock formed and the strain it has experienced. Each step in the process is important and adds a new layer of information. The collection of samples provides the raw data. Optical microscopy offers a close-up look at the rock's composition and structure. X-ray diffraction, on the other hand, gives a deeper understanding of the rock's crystalline structure and formation conditions. So you see, strain analysis is not a single process, but a series of steps, each contributing to a greater understanding of our planet's history. It provides a peek into the past, shedding light on the forces that have shaped our world. It's a fascinating journey, from the rugged terrains where samples are collected to the high-tech labs where they're analyzed. Each step is crucial, revealing different pieces of the puzzle that is Earth's geological history. Now, what exactly are we looking for when analyzing strain? Let's dive in and explore two key types: deformation and distortion. Deformation is a term that might sound familiar. It's used to describe the overall change in the size and shape of a rock. It's like taking a lump of clay and sculpting it into a completely different form. The clay, or in our case the rock, is subjected to various forces that cause it to change its original shape and size. This could be due to tectonic activities like earthquakes or the slow but steady movement of the Earth's crust. Now, imagine a rubber band. If you pull it from both ends, it stretches. But if you let it go, it snaps back to its original shape. That's elastic deformation, temporary changes that revert once the stress is removed. But if you pull it too far, the rubber band breaks or permanently deforms. This is plastic deformation, a permanent change in shape and size, much like what occurs in the Earth's crust under high stress conditions. On the other hand, distortion refers to the change in shape alone, without considering the change in size. Picture this. You have a cube of jelly. Now you press down on the top, squishing it into more of a pancake shape. The volume of the jelly hasn't changed, just its shape. That's distortion. In rocks, distortion occurs when forces act on them to change their shape without significantly altering their volume. It's the subtle differences in shape that tell us a lot about the forces that acted upon the rock. By analyzing deformation and distortion, we gain insights into the history of the Earth's crust. The rocks beneath our feet carry the imprints of the forces that have acted upon them over millions of years. By studying these imprints, we can understand more about the Earth's past, including the movements of continents, the creation of mountain ranges, and the occurrence of earthquakes. In the world of strain analysis, deformation and distortion are the telltale signs of Earth's dramatic past. So, we've analyzed strain in a rock. How does this information help us? Well, let's delve into the practical applications of strain analysis. First off, it's a powerful tool for predicting earthquakes. By studying the strain accumulation in the Earth's crust, scientists can identify areas of potential seismic activity. This knowledge doesn't just help us brace for earthquakes, it also aids in designing buildings and infrastructure that can withstand such forces, saving countless lives in the process. Strain analysis also helps us understand the formation of mountain ranges. Mountains are essentially the result of the Earth's crust being subjected to strain over millions of years. By studying the strain patterns in rocks, geologists can piece together the story of how these majestic formations came to be. It's like reading the diary of the Earth, one strain mark at a time. Now let's talk about tunnels and bridges. These structures bear enormous loads and are exposed to a variety of stresses. Strain analysis comes into play when assessing their stability. Civil engineers use strain gauges to measure the deformation in these structures. This data helps them identify potential weak points and take corrective action before a catastrophic failure occurs. And it's not just about preventing disasters. Urban planners utilize strain analysis to design cities that are resilient and adaptable. By understanding how strain affects different materials and structures, they can create urban landscapes that are not only visually appealing but also robust and sustainable. Strain analysis is also used in industries like oil and gas exploration, where understanding the strain properties of rocks can guide drilling operations. Even in art conservation, strain analysis can help identify the best conditions for preserving priceless artifacts. In essence, strain analysis is a crucial tool that permeates many aspects of our lives. It's not just about understanding rocks, but about using that understanding to make our world safer, more efficient, and more sustainable. From predicting earthquakes to building safer cities, strain analysis plays a vital role in our everyday lives. Let's take a moment to reflect on what we've learned about strain analysis. This powerful tool provides us with a unique lens to view and understand the Earth's geological history. Through the step-by-step process of strain analysis, we've seen how it allows us to measure deformation and distortion in geological structures. This information doesn't just help us understand how mountains and valleys formed, but it also reveals the unseen forces at work beneath our feet. And it's not just about understanding our past. Strain analysis has practical applications that impact our everyday lives. From predicting the likelihood of earthquakes to aiding in the extraction of natural resources, this technique is a fundamental part of modern geology and geotechnics. Through strain analysis, we not only unravel the secrets of Earth's past but also prepare for its future. It truly is a window into the unseen power of our planet. Thanks for watching us share our videos, subscribe our YouTube channel and press the bell icon, and stay curious for new uploads.